Alright, so last time we talked about conjugate, and hopefully you have a good grasp of the conjugate now. If not, go back to the last lecture. Now we're going to finish this chapter up and do a lot of practice problem. Now, here is what we're going to talk about today. Hydrofluoric acid, okay, weak acid, which means in water is going to have an equilibrium. And it's going to break up into H plus and F minus. So far so good? Okay. Now, every weak acid and base, what they are going to have an equilibrium, and because they have an equilibrium, they're going to have an equilibrium constant. And this would be Ka here, because hydrofluoric acid is my acid. And the Ka would be product over reactant, so H plus times F minus over HF. Again, I did H plus instead of hydronium, just so it's a little bit simpler. So far so good? Okay. Now, if you remember, we said that F minus is the conjugate base of hydrofluoric acid. We said weak acid, the conjugate of it. And what's the conjugate again? The conjugate is a species after you lose a hydrogen. So when a hydrofluoric acid loses a hydrogen, F minus is considered the conjugate of it. And we said that if you have a weak acid, the conjugate, after you lose a hydrogen, this is a conjugate. The conjugate is a conjugate base. It acts like a base, right? So F minus, which is the conjugate of hydrofluoric acid, is a conjugate base because it acts like a base. Now, what does it act like a base? Because again, it has a minus charge. When you have a minus charge, that means you have extra electron. You have extra electron, you are acting like a base, right? Because base has extra electron to be able to afford that hydrogen. Okay, so, and then we said that this also has a hydrolysis in the solution, right? It has a hydrolysis in the solution because F minus is considered a base. Now, water would be considered an acid, right? So, base is going to get a hydrogen. Acid is going to lose a hydrogen. So, what I end up with is HF plus OH minus. So, that is my hydrolysis. Now, because this is a base now, it's a conjugate base, it acts like a base. What I need Kb. And this was something I struggled when I was you guys a long time ago. That, remember, conjugate base still going to act like a base because it's a base. Think about it that way. So Kb I need, and the Kb would be hydrofluoric acid concentration times hydroxide concentration over F minus concentration. Don't forget we do not include water since it's liquid in the equilibrium equation. Okay. Now, here's what I'm going to do now. You guys ready for this? Here's what I'm going to do now. What I'm going to do, so this was the Ka for HF was H plus times F minus over HF. And then the Kb for the conjugate of that was HF times hydroxide concentration over F minus. Okay? I'm going to multiply this together. If I multiply this together, again, this is a Ka for a hydrofluoric acid, and this is a Kb for the conjugate base of hydrofluoric acid. What could I cancel out? What can be canceled out over here? Help me out. What could be canceled out is the F minus, right? I can cancel out F minus. What else? I can also cancel out the HF. Interesting. If I cancel those out, what do I end up with? I end up H plus times OH minus. H plus times OH minus. What is that? You know what that is. That is K. That's Kw, right? So what did I just show you? What I just showed you was that if you have Ka times Kb is going to equal Kw. How crazy is this? Pretty crazy, right? So here I had a Ka of hydrofluoric acid, Kb of the conjugate of that. When I multiply them together, these cancel out. I show you that what was left over was H plus times OH minus, which is a Kw. So here is the relationship between Ka and Kb. Ka times Kb equals Kw. So if you have one of these, you can figure out the other one, because you know that Kw is a constant, it's 1.00 times 10 to the minus 14. Yeah? Okay. That's not bad, right? Okay, so I want you to highlight this and make sure that you understand this pretty well. So far, so good? Okay. Now, there's one more thing. There's one more thing that I want to talk about before we do practice problem. The next thing, and then we've talked about all the concepts and all the relationship, and then we can just keep doing practice problem. pKa and pKb. Okay? Let me put up two weak acids. Formic acid, a weak acid, and hydrofluoric acid. So weak acid have equilibrium, and we mentioned that weak acid, they all have a Ka value, right? They all have a Ka value. Ka value for formic acid is 1.8 times 10 to the minus 4. The Ka value for hydrofluoric acid is 3.5 times 10 to the minus 4. Now, here's a question that I want to ask you. Which acid is stronger? Formic acid or hydrofluoric acid? Now, don't answer me that just yet. Just tell me, to figure out if the acid is stronger, what do you look at? When I give you weak acids and I'll ask you which one of these weak acids is a stronger acid, then what you look at the Ka value, right? And if I'm giving you weak bases, you look at the Kb value, because what Ka value tells you, again, Ka is product over reactant, and the product is hydronium concentration. So Ka tells you how much hydronium, how much H plus was dissociated. And H plus, hydronium, is what makes something to be an acid. So the more hydronium you have, which means the larger the Ka value is, the stronger the acid is going to be. You know this pretty well, yeah? Okay. Now here's the problem with Ka. Ka is great. You have a Ka. You can look at the Ka to see how much H plus and hydronium was dissociated, and then figure out the strength of an acid. Now, what I don't like about it is that the Ka constant is usually something between 10 to the minus 3 to 10 to the minus 6 value. They are very, very small values. Okay? Now, when you have small values, when you're trying to compare and look at the acidity, it's not very intuitive, is it? No, it's not very intuitive when I'm looking at such a small values. So to make it more convenient, what they came up with was a pKa and pKb system. Now think about it. Remember, like a couple of lectures ago, we said, talking about the hydronium concentration, the hydroxide concentration wasn't very intuitive, and they came up with a pH scale, which is much easier to understand. This is the same thing. When you look at the Ka value, they're not very intuitive. They're just very small values, and so they came up with another system, which is pKa and pKb, to express the acidity of the weak acid, to express the acidity of the weak acid or weak bases. So what pKa is minus log of Ka. What pKb is minus log of Kb. So fairly easy to figure out the pKa and pKb, and it's a better way to express the acidity of the weak acid, or the basic, how basic the weak bases are. It's more intuitive because the numbers are going to be a little bit nicer number. So here's what I want you to do. I want you to figure out the pKb of formic acid and pKa for formic acid and pKa for hydrofluoric acid. Again, it's minus log of the Ka value. So, pause me, figure out the pKa for those. So hopefully what you got was 3.74 and 3.46. Okay, When we give you the Ka, you take the minus log of the Ka, we can figure out the pKa. The same thing as pKb minus log of Kb. So far so good? Okay, now let's go over the relationship of pKa and pKb and all that. So these were the pKa values, minus log of the Ka. Not too bad. So if you remember what we had said that when you look at the Ka value, right? When you look at the Ka value, the larger the Ka value means the stronger acid, right? Because the larger Ka value means more hydronium was dissociated. And if you look at this, the larger the Ka value means the smaller the pKa value and means the stronger the acid. So here is the take-home message. Larger the Ka value means a stronger acid. Lower the pKa value means a stronger acid. And when you look at this, when I was comparing these two to figure out which one is my stronger acid, then I would have to go with the one with the larger Ka, which is this one. But again, looking at Ka with all these such super small values, 10 to the minus 4, 10 to the minus 4, is a little bit harder for me, a little bit less intuitive to figure out. But pKa is very easy. I'm looking with a value of pKa that is lower, 3.74 versus 3.46. 3.46 is a lower value, is a lower number, so that's going to be my stronger acid. So which one is my stronger acid? Hydrofluoric acid is my stronger acid. So far so good? Okay, so what I needed to remember, don't forget this, Ka times Kb equals the Kw, okay? And I need you to remember this one. I need you to remember the pKa and pKb, which is just minus log of Ka and minus log of Kb. Not too bad. And higher the Ka means lower the pKa, means the stronger the acid. Okay, beautiful. Now, are you ready to do some practice problem? Let's do it. Actually, let's not do anything yet. There's one more thing I want to mention. And so over here, I show you the relationship between Ka and Kb. There is also a relationship between pKa and pKb, which you can probably see for yourself right now. So Ka times Kb was equal to Kw, right? And then pKa and pKb is when you take the log of that. So you can probably say it to me right now. Here's a relationship between what pKa and pKb. pKa plus pKb would equal 14. pKa plus pKb is going to equal 14. Yes. Okay. So if you have a pKa, you can figure out a pKb and vice versa. So far so good? Okay. Now you have everything. Now we can start doing practice problem. Here is our first practice problem. What is the pH of a 0.150 molar sodium fluoride solution? And I give you the Ka value. Alright, I need your full attention for this one. This is interesting, isn't it? It's kind of interesting because I give you sodium fluoride, which is a salt, right? Sodium fluoride is a salt, it's an ionic compound, Na plus and F minus. So I don't give you an acid, I don't give you a base to figure out the pH. I give you a salt. What am I doing here? So here was the deal. So I don't give you an acid, I don't give you a base to figure out the pH, which is how we've been doing them. I give you a salt. Well, you know how to do this. Sodium fluoride is a salt. And it has 100% dissociation in water, right? All the 1A group, they would break up in water, fully break up in water. So it would break up into Na plus and F minus. You guys are good with me so far? Okay. Now, when you look at the F minus, what can you tell me about the F minus? Think about our last lecture. F minus is what? F minus is the conjugate of hydrofluoric acid, and we said conjugate of a weak acid, they are basic, is a conjugate base of hydrofluoric acid. You follow me so far? Okay, so I have this salt which is Na plus and F minus. Now when I look at F minus, I go, wait a second, F minus is the conjugate base of hydrofluoric acid. And I said a minute ago that when you have a conjugate of a weak acid is a conjugate base, this is going to act like a base, right? This is going to act like a base. So I can do hydrolysis, right? I can write hydrolysis for this. So F minus plus H2O, I'm going to write a hydrolysis. Because again, this is going to act like a base, so I can do hydrolysis for it. So F minus is my base. If F minus is my base, that means water is going to be my acid. The base is going to get a hydrogen. The acid is going to lose a hydrogen. Nothing has changed. You guys got this down. Plus OH minus. So far, so good. Okay. And hey, every time we have equilibrium, an equilibrium equation, what do we have to do? Yes, ice is back. Ice table is back. Okay. Now, hold on. What am I going to do here? What is my initial concentration of F minus? What is my initial concentration of F minus? Now, check this out. The sodium fluoride concentration was 0.150 molar. Now, sodium fluoride is soluble. Is a soluble salt. It's 100% dissociated in water. So, if I have 0.150 molar sodium fluoride, every single sodium fluoride is going to dissociate. So, how much F minus do I end up having? Yeah, the same number, because every single sodium fluoride is going to dissociate into sodium plus and F minus. And then of course is 0, 0 at the beginning, and over time this is gonna disappear and some of these are going to appear. So my equilibrium will be 1.50 minus x, x and x. You've seen this, nothing you hadn't seen before. So far so good. Now here's where it gets a little interesting. This is why I've been emphasizing this. So F minus is a conjugate base, and as you can see, conjugate base acts like a base. It ends up having a hydroxide in the solution. If you end up having a hydroxide in the solution, which means you're a base, what do you need? You need K. You need Kb. You need Kb, not Ka, because again, like I said before, conjugate base is a base. You're going to treat it like a base. So I need a Kb. Well, we have a problem. I don't give you the Kb, I just give you the Ka. What was I thinking? Except you know how to convert Ka into Kb, right? Because we said that Ka times Kb equals Kw. You guys follow me so far? Okay. So then that's okay. So now we know how to convert this. I need to figure out a Kb. So Kb is going to equal the Ka, which is 1.00, sorry, Kw, 10 times 10 to the minus 14, over the Ka, which is 7.2 times 10 to the minus 4. You guys follow that? I know I confused you for a second. So Ka times Kb equals Kw. And I'm looking for Kb, so it would be Kw over the Ka. I'm going to get the Kb. So far, so good. So if I do that, what I end up getting is 1.39 times 10 to the minus 11. That is going to be my Kb. Okay, so now we are back in the business. Because here I have an equilibrium, so I'm going to set up an equilibrium constant. The Kb is going to equal what? It is going to equal x squared over 0.150 minus x. Okay, because remember again, it is product over reactant. So I have x times x, that will be x squared over 0.150 minus x. Now, the Kb is 1.39 times 10 to the minus 11. It's such a small, tiny number, right? So again, I can assume this x is 0. I can assume this x is 0 because whatever this number is so tiny compared to 0.150. And if I assume this x is 0, then the math is gonna get a lot easier. So you do the math. If you do the math, what's gonna happen is And let me write it out. So it'll be x squared over 0.150 equals 1.39 times 10 to the minus 11. So if you solve for x, what do you get for x? If you solve for x, what are you going to get for x is, hopefully you got 1.44 times 10 to the minus 6 molar, right? It's all molarity. Okay. That's good so far. What did I do? Okay, now here's the thing. What does x represent that can help me out? X represents OH minus concentration. That I can use to figure out the pH. Because remember, all these problems, ultimately, what you're looking for OH minus or hydronium concentration to figure out the pH. So what X is going to be my hydroxide concentration. Okay, that's good. I can work with that, right? Because if I have a hydroxide concentration, I can figure out pOH. pOH is going to be minus log of OH minus concentration, which is 1.44 times 10 to the minus 6 molar. You follow me so far? Okay, great. So then I get 5.84 is my concentration of that. And you guys are probably yelling at me to say, don't forget you need one more sig fig. I do. I'm going to put it is 5.842. So far so good. That is going to be my pOH. Okay, how do I figure out my pH? You know how to do that. All you have to do is subtract it from 14. So 14 minus 5.842 is going to give me 8.158. And that is going to be my pH. Okay, this was a big problem. How do you guys feel about this? I think you guys got this down. You know the isotable, you know equality to the equilibrium constant. Now you know how to figure out Kb if Ka is given. And then you know this part. The hardest part is the beginning. How do you get started when you have a salt? How do you get started when you have a salt? Okay, you want to do another problem probably, yeah? Let's do it. Let's do one more practice problem. All right, here's our next problem, okay? Now, if you can pause me, do this on your own, and then unpause me, and then we can go over it together. So, you look at this problem, and it's the same as before. I ask you for a pH, but what do I give you? I give you a salt, right? I give you a salt, okay? NH4Cl, I give you a salt. Now you have to figure out what is going to be the pH of this. Now this time, we're going to do something a little bit different. Before I show you the math, what is the pH and figure out a value for pH, you can actually kind of figure out if the pH is going to be acidic or basic before doing the math. And that's actually important for you to be able to do that. Okay, ammonium chloride is a salt, yeah? And then the first thing I want to say that ammonium chloride is made from ammonium and made from Cl minus. You can follow that so far? Okay, so far so good. Now, where does the ammonium come from? Where does the ammonium come from? And where does the Cl minus come from? What are they conjugate of? When you look at Cl minus, the Cl minus is a conjugate of what? HCl, right? Is a conjugate of HCl. Now, ammonium is a conjugate of what? Is a conjugate of ammonia. Now, one thing to kind of think about, when I give you a salt, to look at the conjugate, the first one is usually the conjugate of a base, and the second one is a conjugate of an acid. Okay, so you know that comes from a base, comes from an acid. You go Cl minus, okay, that's the conjugate of hydrochloric acid. Ammonia, okay, that's the conjugate of ammonia. I know this is the first time you've seen this. Don't worry, we're gonna do a lot of practice problem like this. All right, so when I do this, then I go, okay, if you have hydrochloric acid, that's a strong acid. So hydrochloric acid is a strong acid. the conjugate of a strong acid is neutral. So Cl minus is not going to do anything because the conjugate of the strong acid is neutral. What we're looking for is a conjugate of the weak acid or weak base. Because if you have a Cl minus, the Cl minus doesn't really do anything. It's neutral because it's a conjugate of a strong acid. Because this is a strong acid. Okay? Now let's come over here. Ammonia. Ammonia is a weak base. If I have a weak base, what's going to have the conjugate? If I have a weak base, the conjugate is going to be a conjugate acid, right? This is going to be acidic. Because if I have a weak base, the conjugate is going to be an acid. So what do I have here? I have an acid and I have something that is neutral. What is going to be the pH here? The pH here is going to be acidic. So I'm looking for a pH that is going to be acidic. You guys follow that? Okay. Now, I can almost see your faces go, what? What is this? We haven't done this before. I'm going to, we've done it in pieces. I'm going to summarize it for you here. If you have a strong acid or a strong base, the conjugate is going to be neutral. Not going to make much difference. If you have a weak acid, what's going to happen to the conjugate? The conjugate is going to be a base. It's going to be basic, right? And if you have a weak base, the conjugate is going to be acidic. Remember this. And I've shown you guys it. I've proven to you by using the math that that is how it is, right? Because when you have a weak acid, the conjugate is going to act like a base. When you have a weak base, the conjugate is going to act like an acid. Now, before we do this, before we do this problem, I want to go back to the last problem and see if we could have predicted that before you doing the math and if the math matches up. So here was sodium fluoride. This was sodium fluoride. So let's do this. So this was sodium fluoride. How we would look at this? We would look at this. We would say sodium is Na plus and F minus. Yeah? Okay. Where did the F minus come from? Where does the sodium come from? I said that when you have this, the first one comes from the base and the second one comes from the acid usually. Usually that's the case. So if I have sodium plus, where does sodium plus come from? It comes from NaOH, right? And what is F minus comes from? It comes from hydrofluoric acid. So the first one comes from a base, so it could be NaOH. The second one comes from the acid, is going to be HF. Then I go, okay, hold on a second. HF is a weak acid. Is a weak acid. So if I have a weak acid, my conjugate is going to be basic. So F minus is going to be basic. Okay. Now sodium hydroxide is a strong base, right? Now what happens if you have a strong base or acid? The conjugate is neutral. So this conjugate is just going to be neutral. Okay. I have neutral plus basic. So what do I expect the pH to be? I expect the pH to be basic. Is that what we got when we did the math? Oh, I hope so. Yes. We got an 8.158 pH. We got a basic pH. And that's what we predicted over here, that the pH is going to be basic. Yeah? Okay. You guys follow that so far? Beautiful. Now, we're going to do this now mathematically to figure this problem out. If you want to take a break, you could do that. You can take a break and watch the rest of this video tomorrow because I know we went over so much. But you guys got this. So here's the problem again, okay? So we predicted that probably the pH is going to be acidic, right? But let's do the math and hopefully that's gonna match up with what I've already predicted. Okay, so again, let's do this, you got this. This is a salt, right? And then you're gonna say, okay, I know about this salt. This salt is going to be ammonium chloride, and then ammonium chloride in water is gonna have 100% dissociation. It's gonna break up into ammonium and is going to break up into chloride. Chloride, I'm not very interested in, but what I'm interested in is this one right here, ammonium. Because ammonium is a conjugate of what? Is the conjugate of ammonia. Is a conjugate of ammonia. And because ammonia is a weak base, so this is a conjugate acid. And I'm going to repeat this one more time. Conjugate acid is going to act like an acid, right? Conjugate acid is going to act just like an acid. Don't forget that. So here is, I have a conjugate acid and I'm going to do hydrolysis. I'm going to do hydrolysis because again, conjugate acid acts like an acid. So I'm going to go, and the acid is going to lose a hydrogen, which means the water is a base, is going to gain a hydrogen. Acid lose a hydrogen, the base, which is the water, is going to gain a hydrogen. You know this by heart right now. Okay, beautiful. Now we have an equilibrium equation. Every time you have an equilibrium equation, what do you have? Ice. Yes, ice is back. You have ice. So, I know that ammonium chloride concentration was 0.120 molar, and I know this has 100% dissociation. Every single thing is going to break up and 1-to-1 mole ratio. So what ammonium is going to be 0.120 molar concentration. And then 0, 0 minus x, x and x, you got this down. At equilibrium, 0.120 minus x, x and x. Yeah? Okay. Then you're going to go and say, hold on a second. I have hydronium here, right? I have hydronium here. This is an acidic solution, right? I have a hydronium here. I have an acid here. Ammonium is my conjugate acid. So what I need is Ka. And bad me, I don't give you Ka again. I give you Kb. But hey, you know how to figure that out, right? Because to figure out the Ka, that's okay. To figure out the Ka is going to be Kw over Kb. My Kw is going to be 1.00 times 10 to the minus 14. My Kb is given to you is 1.76 times 10 to the minus 5. So when I do that, what I end up getting at the end, I'm going to end up getting for Ka, I get 5.68 times 10 to the minus 10. You guys are good so far? Okay, beautiful. So then I'm going to come over here. I'm going to say, okay, so I have an equilibrium. I have an equilibrium equation. So what I'm going to say, I have a Ka. The Ka is going to be product over reactant. You notice by now, it will be x times x, which would be x squared over 0.120 minus x, equals my Ka, which is 5.68 times 10 to the minus 10. Then what am I going to do? You're going to love this. I'm going to assume that x is 0 to make the math so much easier. I can do that because the Ka value is so small. Whatever this value is compared to 0.10 is going to be a very, very tiny value. So assume that 0. What you're going to get for x, if you get the value for x, you're going to end up with 8.26 times 10 to the minus 6 molar. Okay. Yeah? Now, what does x represent that is going to help me out? X represent, I can almost hear you, hydronium. X represent hydronium. Now we're back in business because I can use that to figure out the pH. So, what's that going to be? The pH is going to be minus log of the hydronium, which is 8.26 times 10 to the minus 6 molar. Okay, so when I do that, what I end up getting for pH is 5.083 is going to be my pH. Okay, is that an acidic pH or basic pH? That is an acidic pH. Is that what we predicted? Oh yeah, that's what we predicted. We got this down. Yeah. Okay. Nice job. I'm actually not going to give you a take-home problem because I feel like we've done so much today. But next time, I will do a few more problems like this to make sure you got this done. Right now, I think we need a little break from chemistry. I will talk to you guys next time.